to this webinar. On my side, I'm Alcibiades Tramaras. I'm the coordinator of the project. I would like to say a couple of things about the project, and since it's our first webinar, we still owe to do a general introduction about the project before we move on into two of the topics that we're presenting about two specific topics that we're presenting about that project. So our project started in October 2023. We still have another 13 months left before we finish, and we have all our results concluded. We are 13 partners, including 3 large power generation companies like A2A in Italy, PPC in Greece, and EPS in Serbia. We are also there are also quite a few SMEs included in the project specific to the hydropower sector, like Mass Consulting that is participating today, and IMT. And also research centers like IMEN and CERTH and other specific companies for the topics that we're covering. So the main topic of the hydro is digitization of operation and maintenance and digitization of hydropower. The specific objectives that we have are about developing innovative sensors and data technologies for hydropower plants. We owe to digitize maintenance and operation of hydropower plants, but focusing on sustainability. And we want to develop reliable and robust hydropower data solutions as transparent and safe as needed. We also want to develop decision-making tools for operation and maintenance of hydropower plants and clusters in contemporary power markets. And finally, we need to assess the socioeconomic and environmental impact of our solutions. So our expected results at the moment, we are at a phase where we have finalized a lot of the development of the different tools and items that we are preparing within the project. And the next stages are more about validation and testing in the field these results. So one of the main things is about sensors. We have sensors for structural health monitoring and condition monitoring that are capable of monitoring abnormal or abnormal behavior of machinery or infrastructure within the power plant. We are testing some solutions using ultrasonic waves that could prevent biofouling in specific areas of the hydropower plant. And we're also developing predictive algorithms in order to be able to make predictions about whether certain machinery will break down or they're about to fail. That is done by processing historical data from the plants themselves, but also through the sensor data that we will be collecting. Our project also includes underwater inspections using ROVs. Obviously, those images are quite blurry and they are in a very demanding environment. So that requires some kind of image processing, and it also requires some machine learning in order to be able to detect automatically certain defects that that are going to be captured in those images. We're also developing sensors for environmental and biodiversity monitoring. The specific sensors that are being developed covering certain parameters of water quality like pH, E. coli, ammonia, and many other parameters. There are two distinct cases of sensors. We have one sensor that is more about continuous environmental monitoring, and another one that is more about spot checks in the field. It's like a briefcase type of sensor. Obviously, that requires also digitization of historical data in order to be able to compare values. And the plan here is to make an early warning system for water quality. Okay, so another of the main results or tools that we are developing is forecast modeling, and this is about developing AI-based algorithms that can create forecasts, short-term and long-term forecasts about inflow of water into a specific use case that I will talk about in a few minutes. We're also developing digital twin tools and digital twins of specific plants and generic digital twins. And there is also a decision-making platform that is being developed that Pietro from Mass Consulting will discuss in detail about that. And finally, we also have advanced encryption algorithms for all the data that are going to be collected from the plants and the sensors and the digital solutions that we are developing. There are three distinct use cases in our project. The first use case is with PPC in Greece, and it covers the involvement of 3 power plants. And it's more about carrying out installing the sensors for structural health monitoring, getting data, and observing and monitoring certain machinery in order to make predictions about potential failure. There's also algorithms that are being developed for that. We have the creation of a digital twin for one of those power plants for Ilarionas. We're also testing the biofouling probes in one of those plants in the Purnari, and underwater inspections are already being done. We are at the moment dealing more with the machine learning part and teaching the tool about detecting automatically certain failures. And finally, there's a bit of reduced order modeling about grid communication between those plants. And just to put a bit of more context into this, these are some of the locations that we're planning to install the structural health monitoring sensors, like the link rods of the guide vanes in one of the plants, or the drainage pumps, and of course other areas as well. The second use case is in Italy, with A2A participating in that, and WaterJade. Here it is more about creating a digital twin of the whole water cycle of the catchment area between two lakes, the Sauris and Vergennes Lake, collecting historical data, installing flow meter sensors, and creating AI-based modeling and forecasting for short-term forecasts within like 5 days, and long-term forecasts within 6 months. The last use case is in Serbia. It is about collecting historical data from environmental monitoring, and also developing and testing the biodiversity and environmental monitoring sensors in the field, and collecting more data in order to be able to model environmental parameters and biodiversity parameters, and being able to um, make a correlation between environmental parameters and maintenance, when basically a power plant can go into maintenance, depending on uh, depending on the monitoring data that we collect. And these are some of the pictures from the plant that is participating in this pilot. Perhaps, and maybe you might not be able to see it here, but in one of these pictures is where one of those continuous monitoring sensors is going to be installed. So finally, if we could give some more perspective into the structure of our project. At the bottom, we have the physical infrastructure from the hydropower plants where we are installing different sensors, and we're also collecting information from those sensors. So at a higher level, we have the digital infrastructure level of the plants themselves. So we are also collecting data, historical data of different types from those plants that are participating in order to be able to process those data and create machine learning models and make a comparison, I guess, between those two. On a digital twin level, we have different digital twins that are being developed. One for the Ilarionas plant, which is a more it is a reduced order digital twin, and we also have a communication cluster, a grid communication cluster that is being developed between the three power plants. On the second use case, it is more about hydrological modeling and the water flow forecasting, like I mentioned. And finally, we have the environmental biodiversity monitoring on and trying to create a digital twin of that monitoring. Finally, through data processing, through collection of all of this data, um, uh, we need to visualize all of this data and process, obviously, through machine learning models, all of this data. And finally, the top is to be able to carry out or offer decision-making support to the hydropower plants that are participating within the project. And this is where basically we have a decision-making platform that Pietro is going to present later on. So I would say at this moment of time, I'm presenting these slides. Later on in the next webinar, we would like to present a bit more of the results, but since it is the first webinar, we focused a bit more on introducing the project to the audience and then covering some specific topics that we can at the moment. As mentioned, a lot of the work that is being carried out, it is done right now, and it is being submitted right now as we speak within these next 2 or 3 months. So in future, we would like to present more specific topics and be more informative to you. So if you have any questions, let me know.
Thank you, Alkis, for the first of our sessions. So as Alkis was saying, here's the moment for your questions.
Yes, you hear me?
Yes.
Yes.
Yeah. Thank you so much for such of the presentation, for such of the information. Actually, it was very interesting for me. I have a couple of questions. In your research is completely in turbine side or no? MIV is also include in your research or generator also include? This is the one question. Another question is regarding the water quality. What will be affect water quality for the, especially for the sealing, MIV sealing, shaft seal, maintenance seal, or others cooling water system sealing, it will be effect or not? Another my question, any information, any research you have regarding the MIV age or leakage, especially in Tunian site?
Okay. Nasir, sorry about the last question about leakage of what?
About the leakage of the MIV, especially in Tunian site. There is any research is include in this topic in your research or not?
I don't think so. In what you're asking for the last part, I don't think it is included. It yeah, I can say it is not included.
It's not included.
Yes, not in our sets. At least the last part that you mentioned about the leakage.
Yeah.
Okay. So in terms of the other part, if it includes turbine monitoring, um, in terms of the sensors that we are developing, we for the structural health monitoring, all of these sites, all of these plants, they already have sensors that monitor turbine parameters. And due to the nature of being a research project, we tried to be less invasive into the main parts of the or the most critical parts of the hydropower plant. So it was more on the areas that we're planning to install the sensors are more about the drainage pumps or the penstock valve that some of these plants had an issue, or the guide vane link rods. This was most related to the issues that the plants themselves have identified, but necessarily directly on the turbines. The sensors are not planned to be installed in that area. There are data that will be collected from the turbines, historical data, in order to be able to make predictive algorithms from that. But we're not touching the turbines themselves. If that answers your question, at least for the first question. I don't know if was that okay for you, Nazir?
Yes. Yeah.
Okay.
Yeah.
Okay. And then the second question that you mentioned about the ceiling of the water quality, obviously, this is an issue that one of these plants has, and they wanna know what is the level of the water quality in the reservoir that they have. It is something that perhaps implementing a ceiling does not. It is not affected. Is a bit difficult, I would say, because there's a lot of anthropogenic parameters involved, and controlling those is not necessarily easy. So the company wanted to be able to monitor the water quality levels and biodiversity levels a bit more continuously and in a more direct way than what is required by law. And hence, but obviously this is what we are implementing in one of the use cases. It doesn't mean that if you apply these sensors in another site, you cannot implement some kind of threshold values and trigger a certain action to happen if those values happen.
Yeah. Thank you so much. I want to say, uh, if, for example, the water have some small particles, it will be, in my opinion, in my knowledge, in my field experience. So, if some particle is have with the water, it will be effect on the seas. We are face, unfortunately, such of the issue.
Okay.
Yeah.
Okay.
And another one things, in your possible, I don't know, now in time is run in your project, almost half is run. Possible one case study such of in Afghanistan. Unfortunately, is still we are not did any such of research or investigation. If possible, honestly, I can to assist you in here, because in Afghanistan last 4 decades was war. There was no any investigation or research in hydro project, especially in large project. In historically, we have, as per standard, some country is different, but in Afghanistan, the age of turbine in year one power project, we have around 10 years. It's a little bit all of lack of maintenance, all of lack of data, all of lack of information. Yeah, if possible, one case study in Afghanistan.
Um, I think that was not within our control, Nazir, or I mean, it's something that we can forward to the European Union. Usually, these projects are funded based on, well, obviously the European Union funds this, and we try to collect and find use cases within Europe. Um, I guess there are also some of the other non-EU members that are eligible, but uh, I mean, I guess it is something that we can consider or we can forward to the European Union for considering such use cases or such countries like Afghanistan in the future.
Okay,
There
thank you
were,
so much. Thank you so much.
thank you,
Sorry,
Nazir.
I spoke a lot.
That's okay.
Thank you, Nazir. Thank you a lot. Yeah, I just wanted to ping you that we might need to move with the second presentation just to leave time to all the three presenters to discuss the slides and potentially to leave some extra time for further discussion. Okay. So without any other further ado, I think I would leave the floor to Nikolaos Papadakis.
Yeah, thank you very much for the pass. Hello, everyone. Thank you for being here to our Hydro workshop. My name is Nicolas Papadakis. I am a PhD candidate at Institut Mines Telecom at France, at Paris, France. And today I'm going to present you some of our work regarding how we handle digitalization and, let's say, data modeling in our project and what kind of problems exist, how we handle them, and what the future entails. So very, very fast, we all know that we cannot continue, let's say, staying on fossil fuels. We're moving towards more and more sustainable energy. Why? Because it has many advantages, reduces the carbon dioxide footprint of everyone, it affects public health, it provides some energy security to many countries, and also it provides local jobs. And one of these sustainable, let's say, energy giants is hydropower, the one that we are involved in, we are seeing today. More and more, we see that it's becoming bigger and bigger, and hydropower is here to stay. But the difference, of course, is as years pass, that we have a shift towards what we call smart hydropower. Smart hydropower is taking what we have traditionally, the standard power plants, and adding new technologies like Internet of Things devices, AI, machine learning technologies, data analytics, Why? Because it allows us to do many things. For example, as Alki said, in the use cases that we have in the project, we have real-time monitoring and automations. We can have predictive maintenance. We can have ways to reduce the environmental impact by checking what is in the power plant and the surrounding waters and so on. But yeah, and more specific for the hydro, I'm not going to say them again because you already saw it. We have predictive maintenance, digital twins to allow for decision support systems. We have forecasting. We have the real-time water quality monitoring system. But what is common in all the cases is that all of these are powered by data. Now, there are many, many different ways that someone can represent data, can digitalize information. For example, for the building themselves, there are many building information modeling techniques. There exist energy ontologies that are used to represent information for even hydropower plants. And of course, there are ways to represent the devices, their measurements, and so on. But the main problem, let's say, with what already exists is that mainly what exists there is more generic towards the energy sector. And also, this means that it lacks a lot of concepts that we need, especially for hydropower plant components and application. And I'm going to go into detail further on. We do not have, as we have, for example, for smart vehicles, GTFS, a standardized way to represent information. So that would cover everything, let's say, the applications, the static data, dynamic data, and so on. So let's examine first what kind of data we're talking about. To enable applications such as the one that we saw in the use cases and to enable, let's say, smart hydropower plants in general, we want to have context information. What I mean with context data here is that we want to be able to represent the various components of the hydropower plant, as well as specific details about them. For example, there exists a valve that is there in the hydropower plant. It has this specification, has these sensors placed on top of them, and so on. And why it is very, very important to have details about the context of the data. Let's say that there is someone that has a small-scale hydropower plant. They call it small-scale. And there is also another, let's say, company, another organization that has trained an AI model on a small scale, what they call hydropower plants. They say, okay, perfect, we can use it, we have the similar plan. But there exists in the real world what we call context ambiguity. This means that the same thing based on context might mean different things between organizations. So if you did not have a standardized way to explain and represent information, there might be misunderstandings, problems in connecting organizations, and so on. Like we can see that small-scale hydro means a different thing for Brazil, a different thing for China, for the European Union, and so on. So what we want to have here in the project is to be able to represent both static information, that means the component of hydropower plant, various sensors that we're using in the project, in a way that we can enable strong queries over the data, while we do not have this sort of data ambiguity. And how we're going to do this? Through our own defined smart data models. What we do here is that we try to follow some European standardized approach in data modeling, more specifically NVSILD, which means next generation service interfaces for linked data. That is basically JSON, for those that know, like with also linked data, with also semantics, a way to both have property graphs and RDF in the same place. I'm not going to go into detail, but we try to follow, let's say, a European standard for our data modeling. And what this means for us is that we could have a way to both define static data and dynamic data. What we mean with static data, we mean the various components of the hydropower plant, like the dam, the reservoir, the powerhouse, the lines, everything that does not usually change over time, most likely structural details, components that change after many years, let's say. And we have here two things, properties which are very, very specific details about the components, and relationships. Relationships are the, let's say, as the word says, the relationship between the components. For example, this specific hydropower plant has this dam. This dam is part of the hydropower plant. And these are very, very useful because through this, we can do strong queries for our applications. And in the hydro, as you can see in this mess here, because it's also only part of our data model, we have extended some existing more generic data models to be able to represent more information than before. And we have created strong relationship between the data to enable for smart queries that I'm going to show in a bit. What we also do is that we do not also only represent structural details, but we represent also information about both sensors and also what they produce. They're what we call observations. And we have very, 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 let's say, specific details about the sensors we can have, like where are they placed. So we can enable, let's say, applications like if we see that there is a measurement that is different between one placement and another, we can see that there is perhaps a blockage in a specific pipe. And this is based on work that we have published and we have extended, we have published also as IMT. This work, also in this work, we have done what we call a separation between the modeling of the sensor itself and its observation. Why do we do this? Because let's say we have a temperature sensor that observes that is 25 degrees, an application uses this observation to display something, but this sensor breaks down, we replace it with another sensor. If we have this decoupling of information between the sensor and observation, we can do these kinds of maintenance changes without changing our underlying applications. And in the hydro, all this data that we have modeled, while I'm not going to go into detail here, but maybe in another webinar in the future, we suppose that this data that has been modeled is flowed through what we call a federated design. Federation here means that each hydropower plant has control over their data, their modeling, and the flow of the data, and they can selectively share what information they want. They only want to share information about specific sensor, specific components. It's up to them what they want to share, because of course, a lot of data is confidential. And finally, we have done this, of course, in our project on real hydropower plant data. We have created models, we have converted them into our format. Then this includes both static information. Here is fake anonymized version of our data, of course, and real devices that we deploy for the project. And this kind of modeling that we did, as I said before, allows us to do a lot of queries that are important for our applications right now, but also we are thinking for the future. And we are continuously refining our models based on the feedback that we receive from partners. But the models themselves, not the data, we provide them available as open source. And we hope that in the future, it will be something that becomes part of the community as a whole. And I think I managed to stay on time. So thank you very much. And I'm open to any questions that you might have.
Thank you, Nikos. Thank you. Yes, definitely in time. Very interesting and understandable also presentation. Thank you. Again, the floor is to our viewers. For any questions, you may raise your hands and we will give you the possibility to open the mic and pose the question. Okay, we have a question from Jan.
You should be able to. Just a quick question. You were mentioning, thanks for the presentation, first of all. You were mentioning that all the codes are available open source. It's something that will be made available, or something that already exists. And if I would want to get a bit more of like an insight of the available codes and processes, basically, do you have some kind of like reports where you describe what you did or what you will do?
So to answer your question, our data models are available on GitHub right now. But of course, this is something that will be refined continuously as the project evolves. For example, right now we represent some information. We have ways to represent information using our JSON schemas. And this is available on GitHub. But as we get more data, as we get more feedback from partners, this same GitHub is going to have newer data models. And I think it's quite self-contained. It has an explanation of what its property, its relationship in a data model is. And while we do have the more detailed report is unfortunately not available for a public dissemination, even though the data models themselves are. The way that the reasoning behind how they were created in more detail, because it involves a lot of confidential information, it's not publicly available.
Okay. Could you maybe just repost the GitHub in the chat?
You can, if you can also scan the QR code here, you should be able to access it.
Perfect. Thank you.
And of course, if you have any question on the models or anything on the code, feel free to contact me. No, if I had my email everywhere, but never mind.
One thing that I have to apologize, we potentially didn't discuss but, with the presenters, but if the presenters are okay with that, we can also share parts of the slides or the parts that you think it's most convenient, so they can contact you or check what they've seen today. So if that's okay, we will circulate it to all the attendees today, okay?
We came to our last but not least presenter, who is Pietro Mazzaroli from Mass Consulting. So yes, Pietro, the floor is yours.
Hello, everyone. Thank you all for coming to this workshop. The presentation is every drop counts. So in this part, we will talk about how to leverage all this data, all this information to take a better decision about how we use the power plants. So to effectively manage hydroelectric power plants means dealing with a lot of different kind of data, as also Nick was talking about before. And all these data have different sources, have different time references, and different protocols of transmission. For example, we have prices. So we know that in the future, we estimate that in the future, the energy will have different prices in different hours or in different quarter of hours. We have meteorological forecasts, so we know how much, or we can estimate how much water we will have available at our power plants in the future. Or, for example, we have unavailability data, so we know and we can estimate how much our turbine, our machines will be available. And we have also data that are coming continuously in our data warehouse, for example, that inform us about, for example, if the machine has stops or if we have network constraints or network limitation from the TSO. Moreover, we have also data regarding the features of our hydrological grid. So, for example, Nick was talking before about data at a very detailed level. So, data regarding, for example, one valve or one machine in our power plant. But if we have a larger view, we can see that our power plants often are connected into an hydrological grid in which the output of one machine can influence or does influence the income of the whole system. So we have data regarding each part of our hydrological system. We have different data regarding the reservoir that can be daily, weekly, or seasonal. Or we have data regarding our power plants, so we know their max and minimum production. Some can have the capacity to pump water from one basin to the other. And we have data regarding the water pipes that connect one part of the system to the other. For example, we know that the water discharged from one part of the system can become available in the next part only, for example, a few hours later. Finally, we have feature and constraints on our power plants and our reservoir, and we have regulations on these parts. For example, we have the feature of the system that can have constraints. For example, the system cannot be emptied or cannot fill at a higher or lower velocity than, for example, the water level cannot rise or decrease more than 10 centimeters a day or 10 centimeters in an hour for geological constraints. We have constraints of the machine. So, for example, often we see that the machine cannot be started or stopped more than twice a day to reduce the stress. We have a minimum and maximum capacity or minimum and maximum power at which the machine can run efficiently. And we have also regulations on, for example, the reservoir that for example, for touristic constraints, the reservoir cannot be empty at a given period of the year to have, for example, an increased tourist experience. Oh, sorry. So we have all these different kind of data, and all these different kind of data are multiplied by the number of plants that are connected into the same hydrological constraint. So dealing with all these different kind of data by hand can be really difficult. So in this project, we propose a digital system that can contain all this kind of data for the power plants and all the basins. And this system can be integrated with the data sources, so can collect autonomously most of the data that are required. There is one mathematical model that can deal with all these constraints, all of this data, and can provide optimized solution for in terms of production schedule in the future. Also, a digital system can provide easy access to both input data and to the output of this optimization process, so the forecast of the production through the graphic user interface and or through, for example, Excel reports that a person can download from the platform and use or transmit to other people. Also, a digital system can allow an automatic process of import data, computation, and transmission of output, so the load on each person can be minimized or made more effective. This system can be used in different ways. So creating these systems that contains this different kind of data that is able to deal with this kind of data and is able to create output autonomously can be leveraged in for different goals, for different applications. One is planning. So I have the forecast of inflows, the forecast of prices. I can plan my production on the power plants in the same hydrological system, for example, to put the optimal production on the market. Another way is possible to do what-if analysis. So instead of having, for example, one single forecast of inflows or prices, I can have different forecasts of inflows and prices and test how my production changes in accordance with different forecasts. So I can test, for example, if my system is robust to minimal changes in the output. Similar is stochastic analysis. So I can estimate the variance in output according to the variance in the inputs. And also, again, variance analysis. We'll jump to conclusion since we have only 5 minutes left. But so to conclude, as we have seen also from the other presentations, there are multiple streams of data, and these data are very different from one another, and all these data are needed to be considered simultaneously at the same time. The hydroelectric power plants, if viewed as a complete system, they are complex systems composed of multiple parts, and all these parts require these different kind of data to be analyzed. Also, the power plants cannot be used freely, but there are constraints in the management, or there are constraints in managing and in production. So an optimal production must also deal with regulations and constraints. And a digital system can help with managing all these different data from all these different parts to have an optimized production of our system. Sorry, it was kind of fast, but we are approaching the 5 minutes left, so we have some time for questions.
Thank you, Pietro. Yes, and we have a question from Janice on the chat. Yes.
For the optimization,
do you plan to use legacy tools such as stochastic dynamic programming or mixed linear integer methods?
Yes, we used an optimization that is at its core a mixed integer linear method.
And another follow-up question again from Janice is, will there be development of new methodologies?
For the optimization itself, at its core is a mixed integer linear method. We try, let's say this, now I'm talking by experience. We are, let's say, from mass consulting, we are always, let's say, experimenting with different methods. But so far, mixed integer linear and mixed integer linear is the one that gave us the best results, mainly in terms of reliability of the output. So there may be other methods, but one of the requirements we often have is that the system must work and must provide results in a very different, in a wide variety of conditions. The main code, the R&D is, let's say, mixed integer linear is a legacy method, but to apply it effectively at different power plants is, let's say, must be tuned, and for having an effective and, let's say, an optimal solution must be tuned and must be studied for the different power plants. For example, in these cases, in this part, the power plants in Serbia cannot work with mixed integer linear because they gave us the requirements that it must consider also aspects like turbine efficiency. So we create a different model for that power plant in a specific. So also the method at its core is the mixed integer linear, but there are tunings and there are different layers to the optimization process that, let's say, make the computation more complex or makes the model more complex than just applying mixed integer linear.
Okay, thank you, Pietro.
I see another.
Yes, Janice is happy with the answers. Thank you, Janice, for the questions as well.
I see another hand raised.
We have some questions as well from Nazir again. So Nazir, please, if you can turn on your mic and pose a question.
Thank you so much for your presentation. I have a question regarding the gross head. Did you include the gross head data in your case study, or do you thinking the gross head will be affect the optimal energy product or not?
Can you repeat, please?
Yeah, my question is that did you include the gross head data, gross head of the reservoir of the data, and did you think the gross head will be effect on the optimum energy product or not?
Yes, that is one other aspect. If we include the head, so the head of the basin, the water head on the turbine changes with production, because obviously the more I produce, the less water I have, so the less the head, the less efficient is the whole system. This part also circling back to the previous question, is not linear, so cannot be dealt with a simple MILP system, so mixed integer linear programming, but with let's say with more complex systems, or with multiple let's say steps of optimization, this effect can be also taken into account. Usually, this depends also case by case, because usually, for example, in the alpine power plants, the head so the distance from the basins to the power plant is much higher than the let's say the change in water level on the basins. So the effect of taking this into account is small and is not really relevant. So it is can be overlooked, but overlooking this makes the model simpler and more reliable. So it is usually better for the day-to-day operations. In other cases, again, for example, in the Serbian case, where the total head is lower and the machines are really close to the reservoir, this effect must be taken into account. So a more complex mathematical model must be used.
Okay, thank you so much.
No worries.
Quick one, Nasir, I left an answer for you on the chat. I had an answer from Zarko, who works for Reps. So yeah, the water quality does not affect the sales. I left an answer clarification from Zarko regarding the question. I thought you were talking about thresholds, but yeah.
Yeah, okay. Let me check. Okay. Thank you so much.
Okay, as I was saying, we're running a little late. We don't want to keep you the more than the necessary because it's a Friday afternoon. We understand that. So we wish to thank you all for coming. We will send you all the slides so that you will have also the contacts of the speakers and you can touch base with them for the discussions or questions that you might have. The only thing I can tell you is that this is the first of a series of workshops, so we will come and invite you or send information about it from September. I guess now is going to be time for holiday, summer break, well-deserved break. So on behalf of the whole Hydro project, we would like to thank you all for coming and wish you a lovely rest of the day and a lovely weekend.
Thanks also to our speakers, of course, to Alkis, Pietro, and Nikos for agreeing to make this workshop. And hopefully to all the viewers, thank you once again. We hope that you find this interesting, inspiring, and let's keep in touch. Follow the Hydro on our social media, our website, to be updated on our activities, and see you at the next workshop.